Hi everyone. In this lecture, I want to introduce recursion and provide you with a step-by-step procedure for defining functions recursively. Before we talk about recursively defined functions, let's start with something more familiar. For example, consider the function that computes the distance between 2 points separated by a horizontal distance of a and a vertical distance of b. The Pythagorean Theorem tells us that a squared plus b squared equals c squared. And since distance is never negative, this allows us to conclude that the distance c is equal to the square root of the sum of the squares of a and b. Now, since there's a built-in square root function, math.sqrt, we'll use it without knowing how it works. Despite this, we'll trust that it works, and if it does, our function, our distance function that is, will work as well. Now let's talk about recursion. A recursive function uses itself in its definition. Now here we may not understand how it works for smaller inputs, but as was the case with the square root function, we trust that it does and make it work for the current input accordingly. For example, we can define a function to multiply the integers from 1 to some positive integer n as 1 if n equals 1, and the result of multiplying from 1 to n minus 1 times n if n is greater than 1. For example, if we wanted to multiply the integers from 1 to 5, we can multiply the integers from 1 to 4, which is 5 minus 1, to get 24, and then multiply the result by 5 to get 120. When defining it for 5, we'll be trusting that the function indeed multiplies the integers 1 through 4 correctly. And if it does, we know it'll multiply the integers from 1 to 5 correctly. Hopefully that makes intuitive sense, even if it's confusing why we're able to define a function this way. We'll discuss why this works in a later lecture, but for now, let's discuss how we came up with this definition without getting a headache figuring out what we actually need to do and what we can, quote, trust is already done for us. So the first step to solving a recursion problem doesn't involve coding at all. We simply want to draw a table with the first few inputs and the corresponding outputs or answers. The inputs will be placed in the first column, and the answers or outputs we want to get from our function will be placed in the second column. So in every row, the input is n, which is in the first column, and the output, multiply from 1 to n, is in the second column. So for example, in the fourth row, where n is equal to 4, we have our input 4 in the first column, and our output multiply from 1 to 4 in the second column, which is 1 times 2 times 3 times 4, or simply 24. Setting up our table first will allow us to 1, define our starting point for the recursion, 2, identify how we can get from the previous input from the current input, so we can figure out how to access the previous output, which we will assume is correct, and 3, determine how we can combine the previous answer or previous output and the current input to get the current answer. Okay, I know that's a lot. Don't worry, I'll break it down. But let me first make sure that you understand this table. In this first example, we want a function that multiplies all integers from 1 to n. Our starting point is n equals 1, and multiplying all integers from 1 to 1 is simply 1. So our first row consists of a 1 in both columns, 1 for the input and 1 for the output. The next row will contain a 2 in the first column and 1 times 2 in the second column. Again, the input is 2, so we get the answer for this input by multiplying 1 by 2. The next row will contain a 3 in the first column, so we want the answer for 3. So what should be in the second column of the third row? Well, the answer we get when we multiply 1 times 2 times 3, so that'll be 6. Okay, I think you get the idea now. However, I do want to point out that for some problems, to make the pattern more apparent, it may be best not to simplify our outputs. So for example, in the row with 5 in its first column, we'll leave the column unsimplified as 1 times 2 times 3 times 4 times 5. Now the next step, once we have our table and our empty function definition, will be to introduce an if statement. This is straightforward. We simply ask if our input variable, which is n in this case, is equal to the entry in our first row and first column. In this case, we'll return what's in the first row, second column. So here we write, if n equals 1, return 1. This means that if our n is 1, the product will be 1. This is the starting point, or base case, of our recursion. Once we have our if statement taken care of, the next step is to examine the first column of our table to determine how we can get the previous input from our current input. To do this, we'll need to determine the pattern of how we can go back one row in the first column. For this problem, this means asking how we can go from 5 to 4, from 4 to 3, from 3 to 2, and from 2 to 1. In each case, we can see that we subtract 1. This then leads to the next step of adding an else statement, which we start filling in by returning the previous output or answer. To do this, we evaluate the function we're defining, multiply from 1 to, at the previous input, or the n from the previous row. Here we get the previous input by subtracting 1 from our current input n. Therefore, we'll evaluate the function multiply from 1 to at n minus 1. Once we add the appropriate operations to this else statement, we can assume that multiply from 1 to n minus 1 will indeed be the output or answer in the second column of our previous row. So for example, once we add the operation to make this all work, if you're in the row with input 4 and you subtract 1 to get 3, you'll be evaluating multiply from 1 to 3, which you can assume will be 1 times 2 times 3. Again, you can take my word on this for now, but I promise I'll be showing why this works in a later lecture. So let's continue to the next step. To determine what to add to this else statement, we need to first figure out the pattern of what we do with the current input from the first column of this row and this output from the second column of the previous row to get the current output in the second column of this row. For example, if we're in the fourth row with input 4, what do we do with this number and the previous answer in the second column of the third row, which is 1 times 2 times 3, to get the output of 1 times 2 times 3 times 4 in the second column of the fourth row? Well, we take the previous output, 1 times 2 times 3, and multiply it with the current input of 4 to get 1 times 2 times 3 times 4. Now, of course, the pattern needs to work for the entire table, but we can see that it does. We will always multiply the output from the previous row with the input from the current row to get the current answer. So we multiply 1 and 2 to get the answer for 2, which is 1 times 2. This in turn gets multiplied with 3 to get the answer for 3, which is 1 times 2 times 3. This in turn gets multiplied by 4, which is 1 times 2 times 3 times 4. And finally, we multiply by 5, which is the answer for 5, which is 1 times 2 times 3 times 4 times 5. Okay, so now that we have the pattern, we incorporate this in our else statement to get our final function definition as shown here. If the input in the current row is n, then we saw the input from the previous row would be n minus 1, and the answer or output from the second column of the previous row, or at least we assume it, will be what we get when we evaluate the function at this input of n minus 1. So it's multiply from 1 to n minus 1. So we take this output and times it by the current input of n to get the answer in this row appearing in the second column, which will be what we return for multiply from 1 to n. Thus we add a times n to the end of the else statement, completing the function definition we saw earlier. So we're done with this example, even if this is a little mysterious now, right? Well, not quite yet. We still need to test this. Testing functions we define is always important, but it's particularly important when we define functions recursively, since it's often easy to make mistakes when the recursion gets more complicated. For now, we'll keep it simple by logging the answer for inputs of 1, 2, 3, 4, and 5, the inputs that we have in this table. So somewhere below our function definition, you can add console.log multiply from 1 to 5 to see if you get 120. You can replace the 5 with 4, 3, 2, and 1 to see if you get the correct answers there as well. You might also want to try some whole numbers such as 8 that you didn't include in your table. Finally, it'd also be very useful to calculate it yourself given the definition using repeated substitution as shown on this slide. This will give you a better understanding of recursion and whether the function does what you expect it to. So if we walk through this function definition for an input of 5, we'll first substitute 5 for n. Since 5 doesn't equal 1, we'll go to the else statement and see that the answer is whatever the answer is to multiply from 1 to 5 minus 1, or multiply from 1 to 4, times the n of 5. Next, we'd substitute 4 for n. And again, we see that 4 doesn't equal 1. So we go to the else statement and see that the answer for 4 is the answer from multiply from 1 to 4 minus 1, or multiply from 1 to 3, times the n of 4. So at this point, we have the answer to 5 is the answer to 3 times 4 times 5. Substituting for n again, this time using an n of 3, we see that 3 doesn't equal 1, and so the answer for 3 is multiply from 1 to 3 minus 1, or multiply from 1 to 2 times the n of 3, and so the answer to 5 is multiply from 1 to 2 times 3 times 4 times 5. And now, the next time we substitute 2 for n, we again go to the else statement. So we have multiply from 1 to 2 minus 1, or multiply from 1 to 1, times the n of 2, right? And see that the answer is multiply from 1 to 1, times 2 times 3 times 4 times 5. And finally, when we substitute 1 for n, we see that 1 does equal 1, and so we return 1. So with this final substitution, the answer is what we expected, mainly 1 times 2 times 3 times 4 times 5, which is 120. So now that we've completed this example, let's walk through a few more, which will hopefully strengthen your understanding of and confidence for defining functions recursively.